Series exists to help us find a way to add infinitely many terms. So whenever in Calculus 3 that we need to add infinitely many things, we'll be using series for that. Series is a word that's both plural and singular, so I'll say a series as well as two series. And it's interesting to understand how it connects to everything you've studied beforehand. So if you look closely at this notation right here, you're going to see that it's a regular summation notation that you've likely seen before, with one small difference, that the upper limit for the summation is infinity. So let's discuss very quickly what that means. So whenever I do something like n equals 1 to 3 like this of n, so the summation of n from n equals 1 to 3, what this means is that I plug in the numbers into this expression. So I take n equals 1, so that gives me 1, and then I add, and that comes from the sigma notation, from the summation notation, and I add to plugging in the next number, which is n equals 2, and then I plug in the next number, which is n equals 3, and this is the last number that I plug in because it's the upper summation limit, and then I just add the three numbers, and that will be a 6. Of course, I could also have done n equals 1 to 5. I want to say this. Maybe instead of starting at 3 this time, I'll be starting at, say, 4 all the way to 9, and I'll be adding n squared or something like this. And so I'll be adding this time. Take 4, plug it in, that's 16. Take 5, which is the number after 4, plug it in, that's 25. Take 6, plug it in, take 7, plug it in, take 8, plug it in. Take 9, plug it in. So I'm taking each number from 4 through 9, plugging it into n squared, and then I'm adding all of those numbers. You can figure out what this adds up to. What's interesting about this is that because I stop somewhere, doesn't matter how long it takes me to stop, as long as I stop somewhere, this will always add up to a certain number. I'm just adding a few numbers over and over. But here, things are slightly different because I'm not stopping anywhere. I'd be continuing on forever. So that would be 16, 25, 36, 49, and so on, adding over and over and over without ever stopping. Okay? So we need ways to discuss when will this add to a finite number and when will this not add to a finite number. So right here, this is the first example of a series that I'm showing you. One thing to pay attention is the starting value. In most cases, we'll start at n equals 1. So the first number that you plug in is 1, but sometimes that's not going to be the case, like I did with 4 over here. Sometimes you're going to start at a different number, like over at the top, n equals n1. So in most theorems and explanations, I'm going to use n equals 1 as the starting point, but in examples, it's going to be very common that the starting term is not going to be 1, so you have to pay attention to this. Sometimes 0 is also helpful, starting at -1 maybe, but always integers and always in increasing order. So let's discuss when will those things converge and when will those things diverge. So discuss nomenclature for a second here. So whenever you have a series like the one before, you're going to say that you're going to define a new sequence based on that series. So that's actually incorrect right here. So you want to be able to add infinitely many terms, right? But you can only add finitely many for now. So the correct way to do it is this way. You say S1 is just what I get from adding a single term. My iPad's not working well today. Okay, let me see if I can maybe move somewhere. S1 is just to add the first term. Give me a moment. Okay, let's try one more time. Let's say you have that series that we were discussing before. Let's say maybe n squared from n equals 1 to infinity. S1 will be just A1, and A1 is whatever you get by plugging in n equals 1 into this, so it's 1 squared, which is 1. Okay? S2 will be A1 plus A2, so that means you plug in 1, that's 1. You plug in 2, you get 2 squared, that's 4, so S2 is 5. S3 will be A1 plus A2 plus A3, and that will be 1 plus 4 plus 9. And so that will be 5 plus 9, that will be 14. So you can find S4, you can find S5, which means you can always find Sn. Not necessarily with a formula, but it exists as a number. For any n value that you decide to find, you can find what Sn is for that n. One small observation is that when I'm talking about Sn, I can call it a summation. I can call Sn a summation, but I'm not going to make a summation from n equals 1 to n, because that wouldn't make sense. When I say Sn, just imagine that n has already been fixed. So it's 3, for example. So you can't make 3 vary from 1 to 3. That doesn't make sense. You need a new variable. So usually I use k or sometimes I to be something that varies from 1 through that n that you discussed. So with this new sequence Sn, that's called the sequence of partial sums. So it has a name. That's the sequence of partial sums. We can decide if that sequence converges or diverges, right? And so if there is a certain number, and we're going to say this number right here, s, we're going to say limit of Sn when n goes to infinity equals s, a certain real number, then intuitively what's happening is that the more terms I add as n grows bigger, then the closer I get to this number s. And so this means my finite sums are getting closer and closer to a certain number. And so I'm going to say that the infinite sum is that number, okay, at the limit. So I'm going to write this. So I'm going to say that it equals s, and I'm going to say that the series converges when that's the case, and that the sum of the series is s, right? So that's a very formal way to think about it. With the sum the example series that I gave you just now, you can see that S1 is 1, S2 is 5, S3 is 14. This is going to grow forever and ever. So that's not going to converge anywhere as a series. So this means I'm going to say that this diverges. This series diverges, okay? It does not converge, it diverges. And so that's the other piece of nomenclature here they have to be able to use. Whenever the sequence of partial sums does not converge as a sequence, we say that this series diverges, and in this case, there is no sum for me to find because the series itself does not converge. Now, it doesn't always have to diverge to positive infinity like this one does. Maybe the sequence of partial sums just doesn't have a number as a limit, so maybe it just oscillates between two numbers or something like that, but this is a way to make it work as well. All right, let's take a look at a few examples here. So this example says, find the first 5 terms of the sequence of partial sums of each series and use them to determine whether each given series converges or diverges. Grabbing my calculator here because I see an n cubed in there that I'm going to have to calculate, so that's going to be a little annoying. So for A, we're going to add n equals 1 to infinity n cubed. So what's S1? That's just A1, so that's 1 cubed, and that's 1. That's S1. What's S2? that will be a2, a1 plus a2, excuse me. So that will be 1 plus 2 cubed. So 1 cubed plus 2 cubed, I should say. So 1 plus 8, and that's 9. S3, the third term of the sequence of partial sums, is a1 plus a2 plus a3. So that is 1 cubed plus 2 cubed plus 3 cubed. So 1 plus 8 plus 27. So that will be 9 plus 27, 36. S4 equals a1 plus a2 plus a3 plus a4. So that will be 1 cubed, 2 cubed, 3 cubed, 4 cubed. So that will be, just note, right? I don't have to add everything again because I know all of this is already 36. And then I gotta add 4 cubed, which is 64. And that will be 100. So that's the easy sum so far. And then the last one. So I guess I didn't need my calculator at the end. So S5 is a1 plus a2 plus a3 plus a4 plus a5. And so all of this is already 100. So I just gotta add 100 plus 5 cubed, okay? And 5 cubed is 125. So this is 225. So if you box each term of the sequence of partial sums, you see that they get bigger and bigger. And let me move this out of the way here for a second so we get a little more space. So this series diverges because I can see that the numbers grow bigger and bigger. We haven't proved that it diverges. And so when I say determine whether the sequence converges or diverges, throughout the course we're going to need a little more formal reasoning to actually determine something, but we've guessed. For this example, we can just guess. So for now, you can think of this as the very beginning of calculus when we started learning limits, that you look at a table and determine what happened based on that table. That's a guess, of course, because you have only finitely many terms or rows on that table. Maybe in the next row something different happens. So that's what we're doing. But soon, later on, we're going to talk about determining really formally that the series does what it does. Let's talk about B now. B is interesting. I'm not going to do all 5 of the terms on B. You can try and find them yourself if you want. So this is B, the sum of 1 over 2 to the power n from n equals 1 to infinity. So what is S1? That will be 1/2. S2, that will be 1/2 plus a quarter. So I'm plugging in n equals 1 and n equals 2. So I'm skipping half steps maybe here. And so I can add this fraction. And that will be, if I find a common denominator, that will be 3/4, like this. S3 will be 1/2 plus 1/4 plus 1/8. So maybe I can do all 5 on this. It's not so bad. It's 3/4 plus 1/8. So again, I can find a common denominator, and this will be double this one, multiply this one by 2. That will be 7/8. So you can see that they're all less than 1, right? And you can also see that the top of the fraction is going through odd numbers. So my guess is that the next one is going to be maybe 9. I'm not sure, but I'll do the next one to see. And that the bottom of the fractions is doubling. So let's see what S4 is to see if our prediction is correct. And maybe it's not going to be correct. So S4, I'm adding 4 terms now. And so these I've already added. So that's 7 over 8, but then times plus 1 over 16. So I now find the common denominator again. Multiply this one by 2. I get a 14 over 16 plus 1 over 16. And so this is now 15 over 16. So my prediction was wrong, but I now see a pattern that's equally convenient. You see the bottoms are doubling, right? And the tops are always one less than the bottom. You see that? So I see a pattern that I like. And I'll do S5 just to confirm my pattern. S5 will be 1/2, 1/4, 1/8, 1/16, 1/32. So one more. When I plug in n equals 5, 2 to the power 5 is 32. And so this will be everything that I've already added, which is the previous term, 15 over 16 plus 1 over 32. So again, I multiply this one by 2 top and bottom, becomes 30 over 32. With the extra 1, it becomes 31 over 32. Right? So you can see this. Let me move again this down a little bit, and then you get to see that probably Sn equals at the bottom 2 to the power n. You see powers of 2, powers of 2, powers of 2 at the bottom. And at the top, always that same power minus 1. You see that? So I can see a pattern going on here. But then if I try and take the limit when n goes to infinity of Sn, that will be the limit of this fraction. So it will be the limit as n goes to infinity. I can split this into two fractions like this. So 2 to the power n, 2 to the power n minus 1 over 2 to the power n. So this will be the limit. N goes to infinity of 1 minus 1 over 2 to the power n. As n goes to infinity, this gets bigger and bigger. 1 divided by something big gets smaller and smaller. And so this limit will equal to 1 minus 0. It will be 1. The limit exists, which means that the series converges. And more than that, we can find its sum. That's not a rule. Sometimes it's impossible to find the sum of the series. But this time we're able to find the actual sum. Impossible is hard, is a strong word. Sometimes it's just very difficult to do. And that equals 1. Okay? If you think about it, what's happening here is that we're always adding. Just imagine you have a line segment of length 1. And on the first term, you add 1/2. First step, you add 1/2. And there's 1/2 more for you to add. But instead of adding that, you add half of that. So you add half of 1/2, which is 1/4. If I use different colors, it'd be easier to see. So maybe this first 1/2 here is this first distance. And then the 1/4 that you add, right, is this half of what's missing for you to get to 1. And then the next term you add is 1/8, which is half of what's missing for you to get to 1. And the next time, half of what's missing, and half of what's missing, and half of what's missing. You'll never actually reach 1, but at infinity, the more terms you add, the closer you get to 1. So that's what this equation at the very end is telling us, okay? That the sum actually equals 1, the sum of the series. Always pay attention to this. Always pay attention to this starting term here, because sometimes if that doesn't start at 1, the series will still converge, but if you skip a few terms, the sum is no longer going to equal 1. So pay attention to this. Now, the third series I don't need a lot of space for, because that one is very, very simple. Let's see if it fits in here. What's going to happen with this series right here? What's S1? It will be just A1. So it will be n equals 1 plugged in. 1 is odd, so this is -1. S2 will be A1 plus A2. So it will be -1 plus 1 because now 2 is even. And that's going to equal 0. S3 is going to be A1 plus A2 plus A3. So it's going to be -1 plus 1 minus 1. So it's going to be back to -1. And this is going to continue happening. S4 is going to be 0. S5 is going to be -1. So because the terms of the sequence AN, they oscillate between -1 and 1, and because it starts with a negative, the sum of the series, the sequence of partial sums of the series, they're going to oscillate between 0 and -1. So they can't converge. The series diverges. Okay, you can find, can be convinced of that if you need. Think a little more, but that's the idea. Now I want to talk a little bit about the properties of series, only for a few minutes, because every time you see this expression, you have to think of this as the limit of something. So every property that holds for limits should hold for series, okay? Even in determinate forms, such as infinity over infinity, and so on. Infinity plus infinity, or infinity minus infinity, excuse me. Infinity plus infinity is always equal to infinity, but infinity minus infinity is an indeterminate form which you have to lift or handle in a different way. But if the series involved converge, if they converge, then you can simply say that the sum is a specific thing. So all examples I gave you here, this one diverged and this one diverged. If you think about what limits, how limits work, if I have something like the sum of n squared plus n cubed, n equals 1 to infinity, I knew this one was divergent from a previous example, and so this one from a previous example. So I can say also this, not only because they are divergent, but because they diverge in the specific way of going to infinity. And because this is positive infinity to positive infinity, I know this is going to be equal to also positive infinity in the way that they diverged. Just as if I were dealing with limits, because I am. This is a limit, and this is another limit. So I can do whatever I could do with limits before. However, if I have something like this, then this is now, if I split again, then this would be infinity minus infinity. And now this is an indeterminate form. I have to take care of it differently. And throughout the next few days and weeks, we're going to discuss how to deal with more complicated forms that series can have. My last observation is this, that a finite number of terms does not affect whether a series converges or diverges. It will converge the same way if it converged before, and it will diverge the same way if it diverged before. So here, I know this one diverges, but it doesn't diverge because it starts at 1. It diverges because it goes to infinity very, very late. And so even if you start at 5, right, it will also diverge. And even if you start at 10,000 or something, it will also diverge. It doesn't matter how many terms you take away from the beginning of the series, as long as you take a finite amount, the series will keep its same behavior because this equaled infinity. So here is just you taking away 4 numbers from infinity. Infinity minus 4 numbers is still infinity. Even if you take away a bunch of numbers, infinity minus 10,000 numbers is still infinity. Because infinity is very, very large, it's infinitely large. So the convergence and divergence behavior won't change. Likewise, this one converged, we'll say converges. And so even if you take a bunch of terms later, this will also converge. So again, this, we calculated this added to 1. This is no longer going to add to 1 because you took away some terms, but it will remain convergent. So this one, n equals 1 to infinity, 1 over 2 to the power n. This will be 1. But this one, it is not starting at 17. It is not going to be 1. It's going to be something else. You can always do 1 minus the first 16 terms. That works. But it will converge either way. This is going to be an important idea as well.